right, let's take a look at our fourth example problem. So a closed tank contains a vapor liquid mixture of steam at 45 bar with liquid content 25% by mass. Okay, so we're starting with a system at a pressure of 45 bars and a liquid fraction of 0.25. All right, so our quality or the vapor fraction would be 0.75. And so since we're told, we have, our system that's 0.25, um, uh, liquid frac of 0.25, we know our system's at vapor-liquid coexistence, both liquid and vapor are present. So for a single component two-phase system, I have a single degree of freedom. So 45 bar is sufficient to pin down the state of our system. Cool. All right. And then in A, the pressure is going to be changed to 80 bars, and we're asked, what is the temperature? Okay, got it. So to start with, we have a system at vapor-liquid coexistence at 45 bars. And then in A, the temperature is going to be changed to 80 bars, and we're asked what the temperature is. So we're going to have to be able to identify our phase. So what I want to do before I move on to A and B, let's start with the system we have and fully categorize it. Okay, so specifically, I'm going to go look up the temperature. Okay, so instead of a system at vapor-liquid coexistence, I can readily figure out the temperature. And then what I'd like to also look up the specific volume of the saturated liquid, the specific volume of the saturated vapor, and then use those two to calculate the specific volume of my system, right, which is just going to be the corresponding specific value or corresponding specific volume weighted by its corresponding mass frac. So XL times VL sat plus XV times VV sat. All right, and the idea I'm trying to get at is, I have a closed container. So if I calculate the specific volume of my system to start with, we're not told anything about a moving boundary. So if we had a piston cylinder apparatus, right, then the volume could change, but then so would the pressure would remain constant at whatever we have our piston fixed at. So if it's in equilibrium with the atmosphere, right, my pressure would be maintained at 1 bar, but that's not the case here. So what I'm going to assume is I'm going to assume that we have a closed fixed container so that the volume's not changing. So if the volume's not changing, then the specific volume is not changing. Okay, that's going to be my assumption. So I'm going to try and get the specific volume of my system pinned down so that as I move forward, if I need it, then I have it to work with. All right, so I have a pressure of 45 bars. So still have my saturated steam tables open. Hey, and we get lucky this time. 45 bars is on there. Okay, so this is my superheated steam tables. My apology. But remember, this first entry corresponds to vapor-liquid coexistence. So my temperature is 257.44 degrees C. The LSAT is 0.00127. That's meters cubed per kilogram. The VSAT is 0.0441. 0.0441 meters cubed per kilogram. Got it. Okay, so let's go ahead and calculate the volume then. All right, so my volume then. Okay, so if I have a script here, so this is problem 4. So our starting case, so XV was 0.75. XL is 0.25. And then the specific volume of my vapor is 0.0441. Specific volume of my liquid is 0.00127. So then my volume is XV times VV plus XL times VL. So let's save this. Okay, 0.0334. That's meters cubed per kilogram. All right, so I've got my starting system pinned down. Okay, and now we're going to move on to part A. So in part A, our pressure's changed to 80 bar. All right, so now our pressure is 80 bar. And we're asked, what is the temperature? Well, if I had a system at vapor-liquid coexistence, then, 1 bar, or, pressure, specifying the pressure of 80 bar would be enough to pin down the state of my system, since I have just 1 degree of freedom. But here I don't know what the state of my system is. What I'm going to assume is my system's closed, or my system is, rigid and fixed, so that while my pressure is changed to 80 bars, it's still that the specific volume is 0.0334 meters cubed per kilogram. Okay, so I'm going to assume that I have some rigid tank so that the pressure is changed to 80 bars. The specific volume is the same, right? And so now I want to determine what the phase is, and then once I know the phase, I can determine the temperature. Okay, and all this is just, we need to make some sort of assumption. So based on what we're given in A, the pressure is changing, right? So that's not fixed. Obviously, the temperature is changing because we're asked what the new temperature is. So the only other variable I have is I could either assume I have two-phase equilibrium, but we're not told that we have two-phase coexistence at 80 bar. So the only other thing I have to work with is assuming that the specific volume of my system is unchanged. All right, so if I just stick with my superheated steam tables, and 80 bars is on here. So at 80 bars, okay, so 80 bars, I have that VL sat, okay, is equal to 0.00138. And VV sat is equal to 0.0235. Okay, meters cubed per kilogram. So based on these two values, since I see that my specific volume is greater than the specific volume of the vapor at saturation at that P, I must be in a superheated vapor. Alright, so I know I'm a superheated vapor. So now I need to find the temperature. So I'm at 80 bars, and our volume's 0.0334. So what I'm looking for now is I'm at 80 bars. So I'm reading across the volumes, my superheated vapor. So I see that my volume of 0.334 is somewhere 0.0334 is somewhere between these two. Okay, so I'm going to write down the specific volume at 375 and 400. All right, and then you would need to interpolate to find your corresponding temperature, since it must be between there. So if I look at my temperature in degrees C, okay, and my volume in meters cubed per kilogram, okay, the lower value is 0.0323. And that's at 375 degrees C. Okay, the upper value is 0.0343. That's at 400 degree C. Okay, so we need to find our temperature where we have our volume of 0.0334. Okay, so we'll perform linear interpolation. So I'll use MATLAB again. Okay, so part A, I'm going to create a vector of my temperatures. So here we just have 375 and 400. I'm going to get my vector of my volumes, which is 0.0323 and 0.0343. Okay, and so then my temperature is interp 1. First comes my, we call it independent variable, which in this case is volume. My independent variable is T, and I want to estimate the value, or my temperature for where my volume is equal to that value I just computed. Okay, so we estimate a temperature of 388.6562. So our temperature is 388.6562 degrees C. Okay, sweet. So that's A. So we found the temperature. Now B. Okay. So now B, we're told the pressure's changed until the contents become 100% saturated vapor. What is the pressure? All right. So now we're going to have that we have 100% saturated vapor. So we're going to have XV, my quality, is going to be 1, right? We have 100% vapor. So it's going to be a two-phase mixture, right? We're going to be at vapor-liquid coexistence. It's just that we're all vapor, right? We're at the right edge of that PV phase diagram, right? We're right there. And we want to know what the corresponding pressure is. Okay. Well, again, right, I'm going to assume that my specific volume isn't changing, so that my specific volume, which is now equivalent to the specific volume of my vapor at saturation, is equal to 0.0334, and that's meters cubed per kilogram. Okay, and what we want to find is what is the pressure. Okay, what is the pressure for which we have that our vapor is at that specific volume. Okay. Well, one way would be to look at my saturated vapor column, and I'm looking for 0.0334. Okay, so 0.0334, it looks like will be between 55 and 60 degrees C. Okay, so what I'll need to do again is interpolate. Okay, but now I'm going to have a pressure in bars. Okay, and then I'll have, this is technically VV sat in meters cubed per kilogram. I believe the first entry was 55. 55. At 55 bars, VV sat's 0.0356. Okay, with the pressure where I have 0.0334, and at 60 bars, it's 0.0324. Okay. So I'll find my pressures by interpolating. Okay, so again, I'll come back up to MATLAB. This will be part B. So now I'm going to have a matrix of, or vector of volumes, which is just 55 and 60. right? We could do, fancy interpolation, but I'll just stick with 2 points. My vector of volumes, which is now 0.0356 and 0.0324. Okay, and my pressure, so interp 1. So now I'll interpolate with respect in volume again, with respect to now pressure, or I'm going to interpolate in pressure with respect to volume for my volume is equal to that value we calculated in the first part. So you get a pressure of 58.4492. Okay, bam. So again, in this question, right, the key is, as we're told we have a system at two-phase coexistence, and we're given how much is liquid and how much is vapor. And then we're kind of, at an impasse. So here, right, so we know the pressure, right, and so since we're at two-phase coexistence, we can calculate the temperature, and then we know the specific volume of each phase, and can calculate the specific volume of my system. Okay, and then where the question is a little poorly worded is in A, it just says the pressure is changed to 80 bars. What's the temperature? And so where it gets a little tricky is by just specifying pressure, our system's only specified if we are at two-phase coexistence. Otherwise, we need to specify another variable. And so, it can't just be that this is a piston cylinder apparatus, right? Because, so we're changing pressure, but then we're not told that we're increasing pressure till we have a single phase. We're not told that, so we're not told that we're increasing pressure till we have, just liquid. So hopefully that helps.